It does not happen very often, but sometimes you may get a process in which you would like to have no overshoot whatsoever. Welcome back, everybody. I'm going to do a short video to show you how you can go and calculate the PID values to avoid just such a scenario. Once again, the formulas have been given to us by Pessen, so it's just a case of implementing these. Now, what would a practical example be? And the one that I can think about is possibly you're going to have something such as a furnace. I've worked on processes where in the past we'd have to go and melt gold-bearing solutions or products down to at least 1063 degrees Celsius. Now, in a case like that, you don't want to overheat your oven because if your set point was sitting at that point over there and you possibly took the process variable too far, then you could find that by overheating the oven, you are going to damage the bricks on the inside of the furnace itself, and you might have to go and replace those bricks in a very short period of time. So maybe it's better just to take the temperature up and to gradually take it up until you can get to the set point that you're not going to have any overshoot whatsoever. Now, the nice thing is that Pessen have provided us with a set of formula for these conditions. And this you can see on the screen in front of you. They do differ ever so slightly from the Pessen with no overshoot, in that in this case the 0.2 replaces the previous 0.33. The integral is now divided by 3 instead of divided by 2, and the derivative is now divided by 2 instead of divided by 3. I must say that this method doesn't always give me the exact results. So in many cases, you might just want to go and fine tune it afterwards. But nonetheless, we're going to go and implement it and see how we can get it to work. We have said that this is a closed loop tuning method, which means that the controller must be in automatic. And what we would do is we would start off with a low gain value and give it a step change and have a look at the response, with the aim of getting continuous cycles and continuous oscillations. Now, we have used this example a couple of times, so I'm just going to jump straight into the value which I know that works for us, and that's going to be a gain in this case of 8.9, and so we should get continuous oscillations. I've actually taken it a bit too far, so I'm just going to put it onto manual quickly and then try again with a very small set point change. I want you to see that we don't push it so that we have straight lines at the bottom or the top. So I'm going to put that into automatic again and give it a small change. That's much better. And now we can see the continuous oscillations. Now, as in the previous video with Pessen and some overshoot, we've now got the KU value, which is equal to 8.9, and my PU value would be the time of one complete oscillation. In this case, from the bottom to the bottom, 1.5 blocks. Each block is 5 minutes, so we're looking at a value of 7.5. So all you now need to go and do is to substitute that into the formulas and come up with the PID values. Let's take that away and quickly just show you what we are going to aim towards. So we're going to have a KU value of 8.9, and we are going to substitute PU with 7.5, and that should give us our calculations. Now, if I do work that out very quickly, I should get to the following results. I have got a gain value of about 1.78. I've calculated my integral to be 2.5, and I've calculated the derivative to be 3.75. Let's go and put them into the controller. And now that the values are in the controller, we can go and try it out. And so I'm going to drop the set point down and we'll have a look at the response that we can achieve. It is going to give me less overshoot than what we would have had with the previous example that we went and did. I'm just going to take that value up, and if you can see, there is going to be a certain amount of overshoot. Now, this is where something that I said a little bit earlier is the fine tuning needs to come in, and you might just want to go and change it because, of course, we don't want to have any overshoot whatsoever. So once you've got a base value to work from, you can go and fine-tune that base value. Now, in my case, I do believe that the gain value is too high, so I'm going to go and reduce that substantially. I've just taken my gain value and I've divided it by 8. And at the same time, I've gone and doubled my integral value. You might recall that when we did the Ziegler-Nichols loop tuning, we said that if it is too aggressive, sometimes just half the gain and twice the integral is going to give you exactly what you're looking for. So I've just gone for 1/8 of the gain and twice the integral. I have gone and put that in, and now you can see the response that we are trying to achieve. I'm going to take the set point down to quite a low value, and as you can see, there's no overshoot. It's going to ease in quite nicely. And if I was to go in the opposite direction, I should have the same effect. I'm going to take my set point up to about 80%, and let's see what it is going to do. Now, the process variable goes up, and it starts to slow down, and hopefully it is going to move into the value of the set point. So in this case, we're not going to have any overshoot whatsoever. So this ties in with the whole idea of Pessen and no overshoot. Once again, this is a nice, easy reference for you to use if you are going to have any type of tricky process that you may encounter in which you don't want to have any overshoot whatsoever. Great, you have got the link at the bottom for a number of the courses, electrical, instrumentation, and process control that I will be presenting.